this is, let's just go back a few slips. I'm going forward. Okay. This is a picture of an electromagnetic wave, and of course this is just a diagram of it. Nobody's ever seen one unless you count what you see right now, because that's of course light, which is an electromagnetic wave. But anyway, this is the notion, is that it's an electric field and a magnetic field, and they're at right angles to each other, and they're oscillating, and they're moving at the speed of light. In fact, Maxwell's equations predict that if you take 1 over the square root of the electric constant, basically, of the universe, and the magnetic constant multiplied together, that you get the speed of light. This is a beautiful thing. Isn't that a beautiful thing? They had T-shirts printed up at the time that had C is the square root of, or 1 over the square root of mu naught epsilon naught, right? Okay. Now, hold on to your question. Okay. So now what you need to understand is what an electromagnetic wave is, right? So what you do is you put an electric field into a space, and then you collapse it. Okay. And a way to do this would be to have something called like a dipole antenna, right? And what you do is you have a charge, say this is positive and that's negative, and there's an electric field, by the way, from positive to negative. And then in the next instant, you make it go away. Now here's the rub. Electric fields contain energy. You'll do this. It's a calculus thing, and you'll integrate this thing, and energy is conserved. So the electric field can't just go away. Yes? Now, if we take an electric field and we collapse it, the energy turns into a magnetic field at right angles, and this is why we know there's a right angle there. Maxwell's equations predict this, okay? That it's a right angle, and we get no magnetic wave. Now, the magnetic wave looks around and says, kind of like Wile E. Coyote running off the cliff, right? This is the way I picture it in my mind, right? Is there anything holding me up? No.
Please send your newly elected 2A class representative to the...
I need to turn this off. I guess so. Our newly elected one. Huh? Sure. All right. There we go. Okay, now, here's what happens, is the magnetic field looks around and says, gee, there's nothing here to make a magnetic field, so it collapses and it creates an electric field at right angles. It looks around and goes, hey, no charged objects here. It collapses. It makes magnetic field. So it's magnetic field, electric field, magnetic field, electric field. There we go. Now, there we go. Okay, are you picturing this? Are you picturing this? Okay. Now, the question is, what does it travel through? Well, it travels through anything that can have an electric field and a magnetic field, which means that it can travel through nothing. The fact that we see light outside means that light has traveled, so many million miles through a vacuum. Yes? Okay? So this is an amazing thing, is that light can now travel through a vacuum, which brings up an interesting question, which might have been your question, but if it's not, that's okay. Okay? Interesting question is this. Let's suppose we're in the vacuum and there's no frame of reference around to be seen. Yes? And we see a light wave. What speed does it go? Well, that's the answer, right? Is that it always goes the speed of light. But imagine if, say, the light wave is traveling this way and I travel into it. Do I observe it going faster than the speed of light? This happens with sound. If you run into a sound wave, you see it going by you faster than the speed of sound, right? So if it happens with light, imagine that if it does happen with light, what changes in your frame of reference? Either magnets work in a different way or electricity works in a different way, because it's 1 over the square root of 2 fundamental constants, yes? So physics either changes in all moving frames of reference, or the speed of light whenever observed is always the speed of light. Yes? This is an interesting question. Isn't that interesting? We're not going to answer that question today. That's the beginning of the next chapter. Our next unit will begin with that. Okay? We're going to begin with something somewhat more mundane. Yes, sir?
So, taking that diagram up there.
Yeah.
Shouldn't the blue sinusoidal wave, shouldn't they be drifted back
Yeah, I was sure of that at one point. And the reason is that what's happening here is that as this thing is changing, think of the derivative of it. It's the changing magnetic field, right? Remember, we know that it's the change that induces, it's the induction thing, right? It's the change that induces a greatest change in the electric field, yeah? So the changes need to coincide. Does that make sense? Right? I thought you were right too. I was like, oh, that can't be the right picture. And then I was like, oh, it is right. Yeah. 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 So then it's like, this is a question I don't have an answer to. It's like, well, what's the energy here? I don't know. It's like, let's not worry about that. Let's go on to this. Right? Okay. So now, here is the next thing. Here is the electromagnetic wave spectrum. All of these are electromagnetic waves. They all travel at the speed of light, even though we call it the speed of light. It's just really the speed of electromagnetic waves. Okay? And what's interesting is, of course, visible light is the only part of the spectrum that penetrates salt water to any great depth. Isn't that interesting? Isn't that interesting? Your eyes evolved to see light that can penetrate seawater. Does that mean that we are evolved from, did the eyeballs evolve underwater first? Probably they did, right? Or if you're a creationist, it's an amazing coincidence, right? Okay? You know, it's just, there we have it, right? Now, if you look at this thing, this is low frequency, right? Also, by the way, low energy, right? This is high frequency and also high energy. And why there's an energy thing there we're going to get to today. And then I think we had a cheer. Didn't we have a cheer last year, didn't we? Right? Radio waves, microwaves, infrared light, ultraviolet, X-ray, fight, 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 gamma rays, yeah, physics. And when the door's open, so we can really annoy people. Are we ready for this? Are you ready? Is everybody ready? Okay, ready? Radio waves, microwaves, infrared light, ultraviolet, X-ray, fight, 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 gamma rays, yeah, physics. There needs to be like something else, and then you're like gamma rays, da 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 da. Like
I think Gaussian did a gamma rays.
Gamma rays, did he?
Yeah, he like drug out the gamma rays.
Gamma rays. There we go. I love that man. Here we have it. Now, the other thing that we should leave you with also is that this spectrum here, this is in the right order. This is red. This is the large wavelength, which is about 700 nanometers. This guy's flipped, right? I need to take this image and flip it around, okay? So the red is the large wavelength. That's about 700 and some nanometers that we can see. And then the violet is the bright, is the blue end here. And that's the short. That's like 400 nanometers. Yeah, and a nanometer is 10 to the minus 9th meters, right? Okay, so now we are to this thing here, right? And we need some of these guys, right? Okay, so we've got V as F lambda. So really what this means is that frequency is, what is it? It's V over lambda. And for all these guys, it's C over lambda, right? So we're basically, whenever we see V with our wave equation, we put in C, right? C is 3.00 E8 meters per second. That's very handy, right? Visible light is from about 700 to 400 nanometers. Right? And a nanometer is 1 E minus 9 meters, a billionth of a meter. Yeah? Atoms are smaller than that, yes? Atoms are a tenth of a billionth of a meter, which is kind of interesting, right? It's almost accessible, but not quite, right? Okay, yeah. So a tenth of a billionth of a meter is the size of an atom. These guys are way too big to make an image of an atom. Yes, right? We can resolve things with visible light down to about 400 nanometers. Things smaller than that we can't really take a picture of, right? Molecules are going to be tens of these, right? And so we actually made images of molecules, but not with visible light, with electrons. And Megan and Paul are going to explain that next time, how that's possible to make electrons act like waves, which is an amazing thing, right? Okay. And then, notice how small a nucleus is, which means you can't draw a picture of an atom, can you? And that's sad. That's sort of sad, right? Okay. So let's get a little tighter on the board. Okay, so these whiteboard problems are just going to be basically V is F lambda with this. Okay. So the first question is, what's the wavelength of a 91.1 megahertz radio wave? There are two clues. The first clue is use V equals F lambda. The second clue is a megahertz. A megahertz is a million hertz. Yeah. And then the other clue is, what do we use for velocity? Speed of light. There we go. Yeah, yeah.